Welcome friends. Let's first solve the problems we left in part 9. The first problem was, given the function f of z is equal to e raised to root z minus e raised to minus root z upon sine root z, we have to find the nature of singularity at z equals to 0. At z equals to 0, what is f of 0? It is e raised to 0 minus e raised to minus 0 divided by sine 0. That comes 1 minus 1 by sine 0 is 0, that is 0 by 0, which is not defined. But if I find limit z tends to 0, f of z, will get limit z tends to 0, e raised to root z minus e raised to minus root z upon sine root z. If I put z equals to 0, I get 0 by 0 form, which is not defined. So I'll use L'Hospital rule and I'll get here limit z tends to 0, differentiate this term and then differentiate the denominator, which will be e raised to root z into 1 by 2 root z. Minus minus will become plus e raised to minus root z into 1 by 2 root z divided by differentiation of sine root z will be cos root z into 1 by 2 root z. Now I'll cancel this and if I put z equals to 0, I'll get e raised to 0 plus e raised to minus 0 upon cos 0. That is 1 plus 1 by cos 0 is 1, that is 2 by 1, which is 2. This is a finite value. And we have already seen that if the function is not defined at the point z0, but the limit is a finite value, then we can say that that singular point is a removable singular point. You can check yourself that at z equals to 0, we neither have a pole of order 1 nor it is an essential singular point. In the second problem, given the function f of z is equal to z upon sine pi z squared, we have to find the nature of the pole. So here we'll take again the denominator equals to 0. So we'll have sine pi z squared equals to 0. That is pi z squared is equal to n pi. Pi and pi cancels out. This will get z equals to plus minus root n. For n values are 0, plus minus 1, plus minus 2 and so on. When we take n is equal to positive values, we will get z is equal to only plus minus root n. When we take n as negative values, we will get z is equal to plus minus I root n. And when we take n equals to 0, we will get z equals to 0. Now let's find the limit z tends to 0, z minus 0 into f of z. That will be limit z tends to 0, z into z upon sine pi z squared. Multiply by pi and divide by pi, I'll get limit z tends to 0. We'll have here pi z squared divided by sine pi z squared into 1 by pi. And we know limit z tends to 0, z upon sine z is 1. So this limit is 1. 1 into, this is a constant term, it will come out 1 by pi. This is 1 by pi. This is a non-zero finite value. Therefore, we can say that z equals to 0 is a pole of order 1. And we can also see that limit, if you find here limit z tends to root 2 sine z upon sine pi z squared, will get here non-zero by 0 form. This also shows that root 2 is a pole. So we can see that z equals to 0 is a pole of order 1 and plus minus root n and plus minus I root n are poles of order 2. So thus our answer is option C. For the third problem, we are having the function f of z equals to z upon z squared plus 4 the whole square, and we have to find the nature of the pole, or we have to find the singular point as well as the nature of the singular point. So again I'll take denominator equals to 0 and I'll get z square is equal to minus 4 and I'll have z equals to plus minus 2i. Now in order to find the order of this singular point, I'll take limit z tends to 2i, have z minus 2i the whole squared into f of z, that is z into z squared plus 4 the whole square. This is a 0 by 0 form, so I'll use L'Hospital rule and I'll get limit z tends to 2i, differentiation of the numerator, that will be z into 2 times z minus 2i plus z minus 2i the whole squared as it is, and differentiation of z is 1, divided by differentiation of numerator, that will be denominator 2 into z squared plus 4 into 2z. This is again 0 by 0 form. I'll use L'Hospital rule again and I'll get limit z tends to 2i, differentiation of numerator, that will be z as it is into 2 plus z 2 times z minus 2i plus 2 times z minus 2i divided by differentiation of the denominator, that will be 2 2s are 4 into z squared plus 4 plus 2 2s are 4z into 2z. Putting the value z equals to 2i in here, putting the limit here, we'll get 2i into 2 plus 0 divided by 0 plus 4 2s are 8 into 2i the whole squared. This will be equal to 4i divided by 8 into 4 minus 4. So 4 and 4 will get cancelled, we'll have minus I by 8. This is a finite value. So we can say that this z equals to plus 2i and z equals to minus 2i are poles of order 2 because of this 2. In the last problem, we have the function f of z is equal to z minus sine hz upon z cube, and again we have to find the nature of the singular point. So when we take denominator equals to 0, we get z equals to 0. Now here you can clearly see that f of 0 is again 0 by 0 form, which is not defined, but limit z tends to 0, f of z will be equal to again 0 by 0. I'll use L'Hospital rule and I'll get limit z tends to 0, 1 minus cos hz upon 3z square. This is again 0 by 0, so we'll again use L'Hospital rule, limit z tends to 0 minus sine hz upon 6z, 0 by 0 form. So I'll get here again, I'll use L'Hospital rule, limit z tends to 0 minus cos hz upon 6. Now here when I put the limit z equals to z tends to 0, I get minus 1 by 6. This is a finite value. Therefore we can say that z equals to 0 is a removable singular point. Now we are going to begin with residues. As you have seen that in complex analysis we deal with analytic functions, and analytic functions are those functions which are differentiable. If they are differentiable, means their limiting value is independent of the path taken. Therefore integration around any closed loop will be equal to 0. Now a function may be analytic at some points and have singularities at other points. If we avoid the singular points, okay, and just integrate around a closed loop which contains only the analytic points, then we'll get the integration equals to 0. But if we integrate around singular points, let's say we have the singular point inside this integration or curve, then this integration will be 2 pi I into sum of the residues of the singularities inside this closed contour. Now if a function f of z is analytic at the point z equals to z0, then its residue, then the residue of the function at z equals to z0 is equal to 0. Second, if z equals to z0 is essential singular point, then its residue will be equal to 0 or not equal to 0. So how do we find their residue for essential singular points? For that we'll take the Laurent series expansion, and then the residue of f of z at z equals to z0 will be coefficient of 1 by z minus z0 in the Laurent series expansion. If z equals to z0 is a non-essential singular point of the function f of z, then the residue again may be equal to 0 or may not be equal to 0. So to find the residue for non-essential singular points, our first method is, if z equals to z0 is a simple pole. Simple pole means a pole of order 1, then what do we do? we can find the residue of the function at z equals to z naught as limit z tends to z naught, z minus z naught into f of z. We have used this type of equation in as non-essential singular points in the previous video also. And the second method is, if our function f of z is of the form phi of z upon g of z, then what we can do is then the residue of the function z equals to z naught will be phi of z divided by the differentiation of the denominator g dash of z at the point z equals to z naught. But when denominator can be written in factorized form, we will use this equation, otherwise we will use this equation. Now if z equals to z naught is nth order pole, then the residue of the function at z equals to z naught will be equal to limit z tends to z naught 1 by n minus 1 the whole factorial d raised to n minus 1 upon dz raised to n minus 1 z minus z naught the whole raised to n f of z. Point number 4. If z equals to z naught is a removable singular point, then the residue of the function at z equals to z naught is always going to be 0. Now how do you find the residue at z equals to infinity? Given the function f of z, we will replace z by 1 by t and then we will get function f of 1 by t. Now we will consider the function g of t, which is nothing but minus 1 by t squared f of 1 by t. Now we will do the Laurent series expansion of this function g of t about the point t equals to 0. Then the residue of the function f at z equals to infinity will be the coefficient of 1 by t in the Laurent series expansion of this function g of t about t equals to 0. Now we are going to look into two theorems. One is the Cauchy-Integral theorem. If f of z is analytic in a region C, then the closed integration over C f of z dz will always be equal to 0. And the second theorem is Cauchy-Residue theorem. Cauchy-Residue theorem states that closed integration over C f of z dz is equal to 2 pi I into sum of the residues inside the curve. Now in the problem, if it says that this contour C is positively traversed, that means we are having anti-clockwise direction and that gives us plus 2 pi I. So in this formula we will use plus 2 pi I into sum of the residues inside the curve. But if our contour C is negatively traversed, that means we are moving in the clockwise direction, and then at that point we will use minus 2 pi I. So our integration will be minus 2 pi I into sum of the residues inside the curve. Now closed integration over C f of z dz is equal to 0 when? First condition, when f of z is analytic everywhere, then this integration will be 0. Second, if the sum of residues is 0, then also our integration will be equal to 0. Third, if all the singular points are removable singular points, then our residue will be 0, which will give us integration equals to 0. And fourth, if all the singular points are outside this curve, then what will that mean? That inside the curve the function will be analytic. So if we have a curve like this and outside the curve we are having singular points, that then our integration over this closed contour C will be equal to 0. Let's take an example. We are having closed integration over C dz upon z plus 3, where C is a circle in the traversed in the anti-clockwise direction, and we are having mod of z equals to 4. This is the region of convergence, which we know it is written as z minus z0 is equal to r. So r here radius is 4, z0 is the center of our circle which will be 0. So we'll plot a circle with center 0 and radius equals to 4. So plus 4 on this side, minus 4 on this side, and we'll get a circle like this. Now we'll take the denominator equals to 0, we get z plus 3 equals to 0, we get z equals to minus 3. So here we can clearly see that this z equals to minus 3 lies inside this contour C, and we know that z equals to minus 3 is a pole of order 1. Therefore the residue of the function at z equals to minus 3 will be limit z tends to minus 3 z plus 3 into f of z, right? So that will be limit z tends to minus 3 z plus 3 into 1 by z plus 3. So this and this cancels and we get equal to 1. Therefore this integration I will be equal to 2 pi I, since it is anti-clockwise direction, that means it is positively traversed. So we'll use plus 2 pi I into the residue. We are having only one residue which is 1, therefore the value of this integration will be 2 pi I.